Welcome to this GC3 webinar entitled Introduction to Life Cycle and Alternative Assessment. I'm Saskia Van Bergen, GC3 Education Project Lead, and this webinar is part of the GC3 Education Webinar Series, which is being designed to be a webinar-based green chemistry and safer alternatives training curriculum for GC3 members and other companies. For this webinar, we're excited to present three presenters: Ann Blake, Thaddeus Owen, and Tom Etheridge. Ann is the principal and founder of Environmental and Public Health Consulting. Thaddeus is the Chief Sustainability Engineer and Life Cycle Assessment Leader at Herman Miller. And Tom is the Worldwide Life Cycle Assessment and Carbon Footprint Program Manager at Hewlett-Packard. This webinar is scheduled for 90 minutes and will provide an overview of the landscape of available tools and provide examples of how companies are using tools to screen alternatives and assess the life cycle impacts of products. With that, let's get started. Ann?
Thank you, Saskia. Thanks very much for inviting me to speak today. I'm starting first because I'm sort of doing the high-level overview, particularly to alternatives assessment practice, and then my colleagues will follow with how they actually do life cycle and alternatives assessment at their companies. And so what I'd like to do today, what I'd like to cover in the next 20 minutes or so is a definition of alternatives assessment practice, a quick overview of where alternatives assessment came from and why, and how it compares with life cycle assessment, risk assessment, and comparative chemical hazard assessment, with which it's often confused. And then we'll talk a little bit about, depending on who you are, what kinds of tools are available to you and the decision you need to make depending on where you are in the supply chain. And then I'll talk a little bit about the current practice, because this is still a fairly new field, less than 10 years old or just about 10 years old from the original framework that I'll talk about in a minute, and some of the challenges that we're encountering as we deal with the issue of complex decision making around finding safer alternatives. Some of those challenges that I'll be talking about include exposure considerations. Where does exposure fit in alternatives assessment and hazard-focused chemical assessment? And then decision making, complex decision making and trade-offs. How do we trade off things that are not equivalent in any way? For example, carcinogenic potential versus performance and costs and economic considerations. And then finally, data gaps, which are a continuing challenge for all of us in this practice and others. So let me start with the high-level view, which is what's our goal. And our goal here is that we are trying to make safer chemicals, materials, processes, and products for everyone up and down the supply chain, and from manufacture through use phase through disposal of chemicals, materials, and products, with the other bottom line goal of having a viable green economy that utilizes chemicals to create products and services that does not impact the health of people and the planet. Some of the co-benefits that we've found of the work that we do is that we are getting increased supply chain transparency and communication. These are also the challenges, but we are improving depending on the sector. We are getting more penetration in the supply chain on chemicals and their impacts. We're starting to fill the data gap so that we have the most robust assessment available. And finally, as I said, the bottom line being an improvement in human health and the environment as well as economics. So what is alternatives assessment? If I could see all of you, I would ask you how many of you know about it, but since I can't, we'll start from the beginning. So this is the definition from 2005, generated by the Lowell Center for Sustainable Production, and you'll see their framework as well from the same date. Alternatives assessment is defined as a process for identifying and comparing potential chemical and non-chemical alternatives that can be used as substitutes to replace chemicals or technologies of high concern. And I'd like to emphasize here both the potential chemical and non-chemical alternatives. So we are trying to get out of the drop-in chemical idea, although my chemical engineering friends tell me that there is no such thing as a drop-in chemical substitution for a potential chemical of concern, that it actually involves a lot of rejiggering of the entire formulation or material. And so potential chemical and non-chemical alternatives that can be used as substitutes. And why are we doing this? Because they are replacing chemicals or technologies of high concern. So that's the definition. The other piece that I'd like to emphasize about the definition, that the process includes two phases and can be considered a continuous improvement process. It includes the phase of assessment, which is identifying and comparing those potential alternatives for a chemical or technology of concern, and then evaluating, which includes the whole decision-making and trade-off analysis. So there are two aspects to this process. So the question is, why are we doing alternatives assessment? Why has it evolved? Because there are some questions that existing tools were not really good at answering. So why is it different from life cycle analysis or risk assessment? You'll get much more in-depth introduction to life cycle analysis from my colleagues shortly. So I'll just do the high-level piece, which is that life cycle assessment helps to answer the question, what are the environmental impacts of a product throughout its life cycle? And it's very good at doing that. Risk assessment considers a chemical and asks whether it is safe enough. Comparative chemical hazard assessment looks at hazard, dose response, and exposure, as risk assessment does, and says which alternative is safer, what's the safest possible. And finally, alternatives assessment takes comparative chemical hazard assessment and adds in other decision criteria such as exposure assessment and other assessments in a decision framework that evaluates the bigger issue of what a safer alternative is in a complete decision framework. So this is, I'm hoping this is somewhat legible, but if you want to see this in more detail, there is a document available from the Lowell Center for Sustainable Production. This is the same document which defined alternatives assessment, the definition that I provided a couple of slides ago. So this really has created the structure for how alternatives assessment is done, and then the practice has developed from here and tools have been created for each of these elements. So this first chunk at the top with alternatives assessment foundation defines you're setting your goals and your measurable objectives. What is it that you're trying to achieve? How are you going to make those decisions, and what kinds of guiding principles are going to guide those decisions? The second piece of it is the assessment itself, identifying the chemical of concern and the attributes that we want to achieve from our alternatives assessment, and then identify the alternatives that meet those criteria. And then finally, as I said before, we have first this assessment piece, and then we have the evaluation process. So the evaluation includes evaluating and comparing alternatives on those principles that you decided up at the top and the beginning of the process. And you may also include here health and environmental impacts, social justice pieces, environmental, economic feasibility, and technical performance. So this is where the big trade-off analysis comes in. So that was 2005. In 2014, the National Academy of Sciences pulled together a large group of our colleagues, a committee of our colleagues, and looked at the current practice of alternatives assessment and put together a sizable book. And we are happy to provide a link to this. And this report from the National Research Council and the National Academy of Sciences is a framework to guide selection of chemical alternatives. And you'll see here, this is their overview. I'm afraid it's still not terribly legible, but we highly recommend going to the book, even though it is like several hundred pages. It is a very detailed overview of current practice of alternatives assessment and does a fairly good summary of saying, here's the best practice of the structure. The structure will look pretty similar to you from what I just showed you from the Lowell Center. Identifying the chemical of concern, scoping out what the issue is, identifying potential alternatives, and then this actually allows for, if there are no alternatives available, allows for this continuous improvement piece where you can do research to generate alternatives if they do not currently exist. And then we do this evaluation process, assessing human health hazards, exposure assessment, ecotoxicity issues, and then finally integrating all of that information and potentially integrating other approaches, assessment approaches such as life cycle thinking, and then finally making the decision about an alternative for your chemical or technology of concern. So back a little bit to the why of why we do this. We do this because our process for selecting chemicals to date has not worked. We have what we call the regrettable substitution, and we have a large number of them. I've put a few here. I was challenged by a decision analysis colleague to say, well, when we do have errors when we do have regrettable substitutions, what kinds of errors are they? So I've attempted to classify them here, and you probably know many of these, but I think this is helpful to us to show that these are all issues of trade-offs. So this is my rogues gallery of my favorite regrettable substitutions. One was MTBE as a fuel additive in place of lead, which was intended to be reduction in air pollution and ended up contaminating surface water. So that's one we get quite a bit from one environmental medium to another. Also a very common regrettable substitution is from one health impact to another. The example seen primarily is, for example, paint strippers, where we've taken a carcinogen and replaced it with a reproductive toxicant. A very common one as well is moving from the environment to workers. The Montreal Protocol banned CFCs as a propellant, and what we saw, one of the downstream effects was that we saw peripheral neuropathy in auto mechanics that were dealing with aerosol brake cleaners and breathing 7 or 8 cans of them a day, because unbeknownst to the rest of the occupational health world, we'd replaced CFCs with N-hexane, which was actually known as an occupational hazard in other occupations, but not in this particular one. So one environmental medium to another, one health impact to another, from environment to workers, and then one very common one also is from human health to the ecosystem, a big example being pesticides, for example, that come up in runoff. When we find alternatives that are an improvement for human health, they tend to be fairly persistent in aquatic sediment and are detrimental to the aquatic environment. So that's why we do this. So now switching gears a little bit to what kinds of tools are available. There are tools available at different parts of the supply chain. I would have to say there are still sizable gaps for decision-making tools, partly because of our issue with data gaps. This is sort of a little chicken and egg problem there. But there are some tools available to you, and I've here outlined the likely players and the kinds of decisions that you may need to make or information that you may need to provide, and the tools that you have available for you. So the most common things we see are that you are a raw material or component supplier, and you need to provide information to your downstream user or OEM. You are the manufacturer or or assembler or the OEM, and you need to be screening the materials that are coming into your product, your materials and components. At a different level in the supply chain, you are a retailer that has 100,000 or more products on the shelves, and you need to screen those products for potentially hazardous chemicals and keep in mind also who your audience is. Are you selling baby shampoo, or are you selling DIY auto repair kits? Very different exposure potential there. And then finally, regulators. Are you a regulator that has a framework that is trying to drive demand for safer alternatives or find a solution to a specific hazard? One example, for example, is the Maine Department of Environmental Protection that did an alternatives assessment on BPA in food packaging for baby food and found an alternative there. So that's a consideration when you think about what kind of question are you trying to answer. You think about the type of tool available, the type of approach from the LCA risk assessment, chemical hazard assessment approach, but you may also think about what kind of tool you have available for you. This is going to be a very quick overview of the existing tools and who they were targeted for. And if you have other questions, feel free to contact myself or GC3 and we will get an answer for you. The ones that are currently available are Green Screen, which is pretty well known. I think most of you probably know that. It's a tool for chemical hazard assessment across a dozen or more human health and environmental endpoints, and it helps us benchmark chemical hazards. So this is very much a hazard-focused tool, but it also allows us to benchmark chemicals and show progress towards greener chemistry. There are emerging hazard and alternatives tools for different populations. I happen to work on a couple of these, so full disclosure, I helped build ChemHat with the Blue-Green Alliance, which takes information on chemicals in the workplace and summarizes very quickly what the acute and chronic hazards are, as well as alternatives if they are available. It's defined by function in the workplace. So what you're using formaldehyde in pressboard as an adhesive, or you're using formaldehyde in some other as a biological storage medium, or some other thing entirely, you have a different approach to the alternative. There's some emerging sector tools, or tools that have existed for a while. Clean Ingredients is one that is now being held at the US EPA, I believe. Forgive me if that's incorrect, but that was designed primarily for formulated chemicals, cleaning products, and cosmetics. Material IQ comes from the Green Blue Institute, and that covers materials. It provides a tool by which you can compare different materials by hazard. And Ferros was designed by the Healthy Building Network and contains a large number of chemicals and materials that can be assessed, as well as safer alternatives. GC3 has pulled together a number of retailer tools in a retailer portal, so go to the GC3 website to find that. And then there are sectors such as the Outdoor Industry Association and the Sustainable Apparel Coalition that are working on getting more information on chemicals in the supply chain for the textile industry. For the consumer level, another tool that I helped build was GoodGuide, goodguide.com, which ranks products and companies on health and environmental and social criteria, all publicly available data, but assembled in an easy-to-read fashion. GoodGuide also has a retailer buyer tool. There are also some proprietary tools for chemical hazard assessment, Cyvera, Greenworks, and others. If you are a company that wants to look at your own suite of products, or if you are a retailer wanting to look at a whole series of products that you have on your shelves. I'm going to skip quickly over the company ranking tools and the regulatory framework. These are regulatory approaches that may be relevant to you as a company. If you are in Maine or Washington, there are Children's Safe Products Acts that list particular chemicals or particular endpoints of concern and require reporting under those. California is the first state that has gone beyond the European Union's REACH program. It's stated that if you had a chemical of concern, you should do an alternatives assessment, but it didn't really say how. California has taken a step further and is now trying to define what alternatives assessment means in a regulatory context. The Interstate Chemicals Clearinghouse also has, much like the NAS framework, has pulled together all the different approaches in a modular approach to alternatives assessment, and these are useful guidelines if you are either a regulatory agency or a company that is likely to be regulated. We're heading now to some of the challenges of our current practice. One challenge has been that you end up going down a series of rabbit holes if you go on a pure hazard approach and don't consider exposure. And so I was happy to see that exposure assessment was considered, the appropriate role of exposure assessment in alternatives assessment was considered by the National Academy of Sciences. And one of the things that's, some of the areas where you might consider using exposure is that some chemicals that you're looking at for alternatives to your chemical of concern may have inherent properties that contribute to a higher level of exposure and therefore a higher level of risk. So that's inherent hazard sort of leading to an exposure issue. And then if there are changes in particular hazard route of exposure, that's something that you should consider about your alternatives as well, that you may be shifting from something that is an inhalation hazard and ends up being a dermal hazard instead. So even though you've reduced the overall hazard, you may have changed the route of exposure in a way that is harmful. And then finally, integrating evidence related to human and ecological impacts and potential exposure when you're looking at alternatives. So some of the other challenges are, so that's how and when do you deal with exposure? The next big question is, let's say you get all your data gaps filled, or you have many of them filled and you have a sizable chunk of data, and now you're at the stage of choosing an alternative. How do you go about doing that, and how do you go about dealing with trade-offs when you're looking at, so for example, fate and transport of your alternative in the environment versus does it cause cancer for workers, does it do some other thing in the environment that you may not have thought of? So there are decision support tools that are hazard-based. Green screen is one that we've talked about. There are also the more complex decision-making frameworks. One of the ones that my colleagues at UCLA Law and Public Health worked on for the California regulations, California Safer Consumer Product Regulations, is MCDA, Multi-Criteria Decision Analysis. My running joke is I can't decide if MCDA is the disease or the drug that is created to treat it, however. And then also the BIS-NGO Working Group Alternatives Assessment Protocol, which was a precursor to what you've seen at the National Academy of Sciences protocol. We're all sort of struggling with how do we incorporate chemical hazard, life cycle risk, technical performance, and all the rest of that. And so these are the current approaches that are there. You've seen the National Academy approach. I'll show you in a moment this multi-criteria decision analysis approach. And all of these available decision approaches have been incorporated into the IC2 framework that allows you to choose what is the most relevant decision approach for your particular decision. So I'm seeing that I'm running out of time here, so I will continue on. So this is to give you an idea of what green screen does, and then I'll go on to the multi-criteria decision analysis. So green screen is a hazard-based chemical hazard assessment tool, which can be incorporated into a larger decision framework. But what it does do is that it defines what a better chemical is and also what a high hazard chemical is. So depending on the subsets of criteria that your chemical being assessed meets, it meets either this benchmark 1, which is the most toxic, or something in between. I think we have still a very, very short list of the preferable chemical that meets all the low toxicity in the green category there in benchmark 4. But this does have an inherent decision process within it. Multi-criteria decision analysis, this is the model that we built at the Sustainable Technologies and Policy Program. And you'll start to see the complexity here of what we're trying to put together. So here, let's say we have multiple alternatives. We're comparing physical chemical hazards, human health hazards, ecological impacts, environmental impacts, so that's media impacts versus, as my colleague referred to them, the bugs and bunnies, product function and performance analysis, and economic impact analysis. So here you've got non-heterogeneous data that is really not comparable. How do you go about factoring all that into a decision? This is the high-level piece. Here it gets much more complex when you start to fill out the data. You're now comparing, let's say, flammability, biological oxygen demand, functionality, reliability, usability. How do you start trading those things off? So what we did is we created a model that helped to visualize what that meant and what was driving the decision. There's lots of questions inherent in this, of course, such as the relative weighting of each of these. For this particular example, we did equivalent weighting of all these high-level criteria that you saw in that first slide: economic feasibility, technical feasibility, environmental, ecological, and human health impacts, and then also the inherent structure of the chemical itself that we were talking about. Now, this particular example was dry cleaning solvents, garment cleaning solvents. See PERC, green earth along the bottom, wet cleaning on the far right. And what this shows you is that you can see what's driving your decision. So you could skew your weights on human health and environment pretty high, and you'd still find that what really drove your decision may be the economic feasibility of wet cleaning and CO2. So wet cleaning, by the way, the taller bar is the better score. Wet cleaning comes out top, even though it's equivalent in ecological hazards, for example, to many of the other options. It is a much better option than the CO2, which is the other preferable option. So all that to say that we as humans don't deal well with complex decision making, and so we will need to create tools in order to do that, to do alternatives assessment, and this is one of the ones that we have modeled particularly for the California Safer Consumer Products Program, but we hope would be helpful for other alternatives assessment processes as well. The other piece that we did find in this is that you can see where data gaps are affecting your decision, which is helpful, which can help you decide whether you want to go back and fill those data gaps, or if you want to continue and feel like you can make a decent decision even with those data gaps in specific areas. So with that, I hope that that was a useful introduction to alternatives assessment as a practice, and also where it has evolved from, the fact that it is still a fairly new field of practice, and we do have some ongoing challenges as it evolves. And now I'll hand it off to my colleagues, who will tell you how they do it in their companies and some of the challenges that they encounter as well.
Great. Thank you very much, Anne. Great introduction. Next we have Thaddeus.
Great. Thanks, Anne and Saskia. So I'm going to walk everybody through the way that we do material screening and alternatives assessment at Herman Miller. If you're not familiar with Herman Miller, we make office furniture, chairs, workspaces, filing and storage, tables, and the like. So one of the ultimate goals, of course, in alternatives assessment, safer chemistry, sustainability, is creating the safest products possible for everyone up and down the supply chain. So, the extreme example is, a product that you can grow sustainably from the ground and eat because it's entirely safe. And why are we interested in the buildings products industry and other industries in alternatives assessment and safer chemistry? For one reason, we in the buildings products industry recognize that all of us, at least the vast majority of us, are spending 90+% of our time indoors. So from the time we get up, get in our car, get to work, all of this time is spent in this indoor environment around these products that every day we're learning more and more about what's in them and how it affects the indoor air quality and our human physiology. And so as we learn more about this and we learn more about potential chemicals of concern, we want to ensure that the products that we place into these positions where we're all living, working, and playing, as well as healing, are as safe as completely possible. And so from a buildings product standpoint, we look at the people that use and specify and purchase our products. They're pretty savvy, I would say more savvy than the general consumer about chemicals of concern in products. So this is a list that Tom Lent put together from the Healthy Building Network. And you can see a whole bunch of circles. There's a lot of different chemicals of concern. Each independent circle is a list of chemicals of concern from people that we sell product to. And you'll notice that there's a lot of them. Some of them overlap, some of them do not. And we have to obviously pay attention to all of these chemicals of concern to ensure that we're providing products that both our customers want and are as safe as possible. So it can get pretty confusing. And of course, these lists of chemicals of concern are not static, so they're constantly changing. And those are, of course, in addition to regulatory lists, such as things like Prop 65 and other state and national regulations. So the way that we look at chemicals of concern and assessment at Herman Miller, we have an overall sustainability program. A piece of that program is our eco-inspired product design. Within eco-inspired product design, we're looking at things like building products with 100% safe chemistry, using 100% bio-based or recycled materials, ensuring that those products get put into a closed loop at the end of life, and then performing a life cycle assessment on all of our products to make sure we understand the environmental hotspots within our life cycle. So these are the types of things we look at for each product, specifically the chemistry, disassembly, recyclability. We have a very specific chemical of concern list, which I'll go through, and then we perform a life cycle assessment. Now, for some products in the buildings industry, they can be pretty simple. They might be made up of a couple components or even one component and very few chemicals. When we look at building products from the office furniture industry, we tend to have very complex products. And you may not think of a chair as being very complex, but this is sort of, when we're doing an assessment, this is a fairly complex product. And we start with, the base product is the first thing that we do when we do an alternatives assessment or an assessment of chemicals, is look at what products do we want to assess. And it can be an existing product, because certainly we've been developing and selling products from early on in the early 1900s that we invented and still sell today. So those products we're bringing up through our assessment process. And of course, we apply this to all new products that we develop. So once we have the product, we need to create a bill of material. Now that simple looking chair is made up of probably 300 different components. Each one of those components, of course, can have somewhere between 3 and 25 different chemicals inside of it. So the first thing that we need to do is have a very clear bill of material so that we know every assembly, subassembly, and component, what it's made from, and who the manufacturer is. So of course we can then go out to that manufacturer and get the full material chemistry, the formulation of each one of those components, the colorants, the finishes, and the powder coats that are put onto those as well. So this can get pretty complicated. These giant bills of materials can span thousands of line items for a single product. This is just a quick snapshot of that chair completely disassembled into its individual component parts. So there's all sorts of big and small parts that, again, we go find these exact formulations from the people that manufacture those raw materials. The types of data that we tend to collect from our supply chain are things like a first cut of just a technical data sheet and an MSDS to make sure we understand as much as we can about the material from the easiest to obtain information. Those things are often obtainable over the web or with a simple phone call or email. And then we try to obtain a full chemical composition or a full formulation on every one of those materials and components. That is a much more challenging thing to obtain for us. And of course, when you're looking at 300 different components per product, spanning multiple products and multiple categories, it can get to be quite a bit of work to understand full chemistry and to deal with the management on the raw material side to ensure they're comfortable even sharing that data. So the first thing we try to obtain, of course, is the full formulation. And this is an example of our data sheet that we'll send to our suppliers. So we'll know that we're using a specific material, let's say a BASF polypropylene. We would send this to BASF or whatever manufacturer is making that chemical and ask them to fill this out with a full formulation down to 100 parts per million of that material. If we cannot get a full formulation, this form is a little harder to see, but this is essentially what we call a chemical of concern or a restricted substance attestation. So if for whatever reason the raw material manufacturer is unable or unwilling to give us the full formulation, we have a very specific list of chemicals of concern to us, as well as regulated chemicals, that they will have to screen their chemicals against and then disclose if they have any chemicals of concern. This, if you look at this shot of Microsoft Excel along the bottom, are the types of lists that we're screening against when we screen chemicals. So we're looking for our Herman Miller internal banned substances, which are things like PVC, phthalates, halogenated flame retardants, and heavy metals. So kind of the heavy hitters, the things that we really want to make sure we stay away from, we have those on a separate banned list. We then have our own Herman Miller restricted substance list, our chemical of concern list, which is made up of all those overlapping circles that our customers are concerned about that are on things like the EPA chemicals of concern list and a number of other lists. The Annex B chemical list, BIFMA, is our furniture manufacturing trade group. We have created a sustainability standard for products through that trade group that we can certify products to. Within that certification standard is a list of lists of chemicals of concern, and that list of lists is found in Annex B. And that's things from Prop 65 and REACH and a number of other places filtered for things that would be found in the office furniture industry. So we screen against that list as well as against Prop 65 and REACH. So this is what our suppliers are screening against if they fill out the chemical of concern attestation. And this is internally what we are screening against. We have a database internally that we'll enter the formulations into. And oftentimes the chemicals are already in there because we've looked at some of those chemicals in the past. And we are then screening them against basically all of these lists. So we use a very list-based approach today on the way that we screen and assess chemicals. This is a screenshot of our external database, what our engineers and some of our suppliers are allowed to see. It's scrubbed a little bit for some of the data, but we enter all of our information, all the full formulations into a database. That database assigns a score. Now we can assign a score which is color-based. Red for contains a known hazard, yellow or green for no to minimal hazards, and unassessed if we either can't assess the chemistry because we don't have the knowledge or we have not sent that out to a consultant to be assessed. We can then search this database anytime that we get a new material, and we can assess if we've already viewed the material and what assessment it's been given, as well as any specific notes as to what potential things to watch out for might be involved in that material. This database contains today about 4,500 different records of materials that we've assessed. In some cases, that's full formulations. In other cases, it's just an attestation. And in some cases, we may not have an assessment because we can't get an attestation or a formulation, and there will be a note to us about that right in this database. So again, this is how we rank our materials and chemicals that we assess, and it's based on a colored approach so that we can quickly understand by looking at the color where that material or chemical falls within our hierarchy of assessment. And then if we go back to the bill of material, every bill of material for each specific line item has a material ID. That material ID is the specific reference to the database that has the formulation. So I can look at my bill of material for extruded aluminum. I can go back to that ID number in my database and find the full formulation, as well as any specific notes or hazards with that material. So again, this is exactly what we're doing when we're screening. Is we take a very rough cut first of all, and we look for the heavy hitters in our industry that may show up and ensure that those are absent. So things again like halogenated flame retardants, heavy metals, PVC, and phthalates. And then we screen against various lists, and we do use both Pharos and the green screen list translator to get the hazard assessment and to continue to do further refinement of screening of those chemicals that may be present. We also may send out to a third-party assessor like ATOC Services, MBDC, or NSF, especially if we are cradle-to-cradle certifying a product. So we do have some cradle-to-cradle certified products where we're required to send the full formulations for assessment to MBDC. In other cases, we may not understand enough about the chemistry in a specific formula in order to internally assess it. So we would then go out and send that to an external consultant to have them help us assess that material. This is a real quick snapshot of the way we would do an internal assessment. So again, if we find a chemical of concern, we kind of walk through the mapping process of what we would then do. So of course, we would try to find an alternative. So we would first ask the manufacturer if they have an alternative that already exists. Again, if they don't, we can either suggest one if we have information about what would be acceptable. Oftentimes, we're not that knowledgeable about chemistry to suggest alternatives for every chemical. So we leave it up to the manufacturer to help us understand what alternatives are available and whether or not those can either be incorporated into the material as is, whether they have an alternative material they can sell to us with no chemicals of concern, or whether we have to go out and find an entirely new supplier for that material that can provide us what we need. And we've done all of those things at various times. So again, the way we base our assessments is we try to base it, of course, first on hazard, looking at things like the Pharos, looking at the lists that we screen through, and then based on risk and exposure. So there's more to just knowing that a hazard is present to understanding whether or not that poses a risk and how critically we need to remove that immediately, and also based on feedback we get from consultants. And as we talk about risk and exposure, our trade group, BIFMA, is going out and doing studies on chemicals of concern in the furniture and buildings products industry, looking at risk and exposure to determine appropriate levels of different chemicals of concern so that we can use those in our alternatives assessment processes. And of course, Anne definitely touched on this, regrettable substitution. We definitely don't want to just remove a chemical of concern without understanding what's replacing that chemical of concern and doing a screening on it. We've all seen, of course, various things that have been substituted that may not be appropriate. Of course, ensuring that things are PVC-free and BPA-free is great, but if you put BPS in place of BPA, that may not be the best choice, or other chemicals that are not completely safety tested or may have similar safety profiles to the one that you're substituting. It's really important to understand, and it's really challenging because there's not a lot of tools out there that can help us understand really well what the alternatives may be and how effective they are, as well as their safety and health impacts. So again, what we're trying to do as we do alternatives assessment and build our products is to ensure that they stay within either a natural cycle or an industrial cycle, so they can continue to be reused or become food for other organisms without any issue worrying about chemicals of concern at end of life. Real quick example is our fiberglass chair. So we had an Eames fiberglass molded chair that we used to sell. It was invented in the 50s by Charles Eames. And that chair, of course, used the fiberglass material, which uses styrene as a monomer to usually dissolve the resin that holds the glass mat fiber together. And we know that styrene is probably not the best material to be using. But of course, when this was designed and invented, it was during a time period when that wasn't known, and this was one of the better materials to use for durable products. And so what we did at Herman Miller is we transitioned away first from fiberglass to polypropylene. So we began making this chair more environmentally friendly through an alternatives assessment by using the polypropylene material. And as designers are known for, they came back a number of years later and said, we really want the fiberglass design to be sold again. That's the look everybody wants. The polypropylene doesn't look like the fiberglass matte look. And so we had a challenge of trying to find a fiberglass that was a more friendly product that had no chemicals of concern that we could find through our screening processes. Eventually, we found a company that created a fiberglass that was considered monomer free. It did not have any monomer that captured the resin, and we're able to sell the fiberglass chair on the market again using a cleaner chemistry formula through the alternatives assessment that we have put it through. In addition, we made that chair closed loop so that for free, the customer can send the shell back to us at end of life if it happens to break. Of course, these chairs tend to last for a very, very long time, but the manufacturer of this chair will take the material back and reincorporate it into a new product, which is typically very difficult to find for a material like fiberglass, which is technically not recyclable. And this manufacturer has found a way to recycle that material into a new product. And again, these considerations become very important to our company because we do design products that are not just use once and done. We make iconic, durable products that are going to be around a really long time. And if we're handing down some of our iconic products to our grandkids and our kids, we want to really feel good that those products are safe and healthy as possible and that there's no downside to using those products forever. And that's what I have, so thank you, everybody.
Thank you very much, Thaddeus. Great. Tom?
Okay, thank you very much. So thank you, Ann and Thaddeus, for those introductions. I'm going to take sort of a different turn here and talk about life cycle assessment. What you've heard so far is about tools and processes for determining how to make good substitutions for specific materials, either from an environmental standpoint or a toxicity standpoint or something like that. What I'm going to talk about is life cycle assessment, which doesn't do such a good job of helping you make those decisions. But what it does do a good job of is determining where your highest impacts are, sort of the hot spots that Thaddeus mentioned, so that you can start to intelligently look at where to reduce your environmental impact. And I'm going to talk about it from the printing aspect of HP, which is where I do most of my work. So what motivated HP to even start looking at life cycle assessment? I'll go into what life cycle assessment is a bit more in just a moment, but generally speaking, it's a very time and cost-intensive tool to use for products. So to do it on things like printers or PCs or something that has a relatively limited lifetime has typically been prohibitive. But at HP, we've adopted it in the printer business for a few reasons. The first one is the main thing that everybody's after. How do you get information to your designers and your scientists to improve the products, both for what the customer is looking for and for what's best for the environment? It's also, we're using it to produce what are called environmental product declarations, and those are basically summary documents that a customer or design engineer can look at and see, okay, what are the hot spots, how are they determined, and where can I intelligently compare two different products, for example, to see which one's the best. From a very practical and business standpoint, it helps us earn 3 EPEAT points. EPEAT is an environmental eco-label for electronic products that's required by many contracts, particularly governments, in order to sell products to them. So getting 3 EPEAT points was a big motivator for us. It's a very good proactive approach to potential regulatory issues because you can see where the hotspots are going to be for carbon or for water and things like that. And finally, customer demand. I think in most industries, in the electronics industry in particular, there's a high demand from customers to understand what the environmental impacts are of their products so they can compare among different manufacturers to both pick the best product and understand how they can reduce their own environmental impacts. So the challenge is that, as I said, LCA itself is typically both very time and cost intensive. So how do you apply it across a huge portfolio of very complex products without costing a whole lot of money? That's what I'm going to go into more here in a few minutes. But the main thing about that is that we needed some sort of model that we could leverage across these products so we didn't have to do single one-off LCAs for each and every one of them. And it's nothing for a life cycle assessment for a product to cost anywhere from $70,000 to $100,000. And for something that's going to be in the market for 5 years, that's really not very cost effective. So I'll go into the model here in a moment, but first let me take a step back and say, what is LCA? Well, life cycle assessment, or LCA, is a rigorous tool that's guided by certain ISO standards for assessing the environmental impacts in several different categories of any product over its life. What life cycle assessment attempts to do is take everything from pulling the raw materials out of the ground to manufacturing the product, shipping it to customers, all the packaging that goes into that, all the transportation nodes, the actual use of the products, which in our case, as you'll see, is a very, very significant part of the life cycle assessment. And finally, toward the recycling or landfilling of the product at the end. The process itself, like I said, is governed by several different ISO documents that describe in detail how you go about this to ensure that if you're doing it, everybody that's doing it is doing it in the same way. The main thing to think about if you're looking at a life cycle assessment is something called the functional unit, and that's basically the way you determine what the use is of that product that you're going to report against. So you could imagine for a television set, it's watching a program on cable for an hour. Well, for printers, we define it as the impact of printing 1,000 pages, and that'll become critical in a few minutes, and you'll see why. So first thing we have to do is model this whole thing. How do you take a printer and model it over its entire life? So for production, you have to consider all the components and the assembly of the product. You have to consider distribution to customers and distribution of parts within the network. For our work, and what I'll show you here in a few moments, we're looking at distributions to the U.S. market because, as I mentioned, we're looking at it for EPEAT, but the model can be modified to use for any market in the world. Use phase. As I mentioned a minute ago, use is huge when it comes to printers. Think about paper and cartridges that go in, the electricity that goes into doing that, and all the distribution and packaging of all those cartridges and that paper, and electricity for that matter. And finally, end of life, modeling getting the product to its final recycling or landfilling destination, and then what do you get back if you have recyclable materials in there? For instance, a LaserJet printer has a lot of steel in it. Well, most LaserJet printers, fortunately, don't go to landfill. They go to recyclers, and so you get some credit back for recycling that steel or some of the plastics in there and things like that. So what we at HP did that's unique, we think, within our industry is we worked with a company called PE International, which is now called ThinkStep, to do an LCA that's an overarching LCA for our printer fleet in general. So rather than doing it on an individual product basis, we said, look, printers all have certain basic components that are similar from one to another. Why don't we do a sort of a grand LCA that takes all that into account rather than doing it for each and every product? It was a very unique approach. It was also a very expensive approach at the outset, but in the long term, it's been very cost effective on a per product basis. What this LCA does then is it says when we run one of our products through this model, here's what goes in, here's exactly how it's modeled, and here's how the data is produced, just like you would expect with any LCA report. So the challenge at the printer level, as I mentioned earlier on, is the complexity of the device. And there's certain things that are core to each and every printer. It's going to have a paper feed mechanism. It's going to have some way of putting an image on a piece of paper. It's going to have its basic packaging and things like that. But there are other things which are not on every device, things like high volume page input and output devices, scanners, fax machines, all those kind of other things. So the real challenge here was how do you write an LCA that covers all of that without creating this huge unwieldy document or tool that looks great on the surface, but it's unusable. But we did, with the help of the folks at PE and the fact that we still at HP design and manufacture most of our printers ourselves rather than just buying components, is we took a modular approach. We said, look, we know what all the things are that are going into these. We know how they're manufactured. We should be able to build a model that's modular that allows us to plug and play here. So I can take anything from a simple printer that's just a monofunction device that doesn't have a fax machine in it or doesn't have a scanner and use that as a core and then maybe add some of these other things to it. And so that's what we did. You can see that we started with LaserJets as the first ones and all the different things that go into that, and then realized once we had done it that we were pretty close to being able to do it for most any of HP's imaging devices. So we took that model and added to it specific things that are unique to inkjet, the cartridges and print heads and so forth that go there. and created sort of a grand model that can be used to generate these LCAs. I'm not going to show you too much about that model, but it's basically a web-based tool. It has about 1,500 lines in it where somebody like me can plug in anything from the packaging for that machine, what its transport nodes are, how many cartridges it uses, how much power, and so forth, and generates an ISO-compliant environmental product declaration that we can use to determine what the hotspots are for these particular products for our customers, and, as you'll see in a minute, for groups of products. So, as you've heard from Thaddeus already, and somewhat from Ann too, your model in these cases is only going to be as good as the data you have going in. So Thaddeus showed you, they assemble at Herman Miller bills of materials that are comprehensive to go into their products to determine this. We do something similar, particularly for things like mechanical parts and cartridges and ink and things like that. But in many cases, we don't necessarily want to break down a printed circuit board to each and every little component. So in those kind of cases, we use data sets that are standard throughout the industry for what a typical circuit board will have on it for that size and so forth. So the model itself is based on several different kinds of databases, some of which are proprietary and unique to HP, and some of which are general industry standard databases that can be applied to any electronic product. So the EPD that comes out is certified by UL Environment, and if you're familiar with LCA, this is basically the nuts and bolts. It's the executive summary or the results part of the document. So for any given printer, you have a small document that reports the recipe midpoints. Recipe is a pretty standard LCA tool. The midpoints being what the outputs are. What's the carbon footprint? What's the water footprint? What's the aquatic toxicity and so forth? And it does them in a format that's consistent from product to product so that anybody can easily compare the results side by side rather than having to read through a big LCA and find the discussion section and pull the data out independently. And you can find one of these LCAs for one of our products on the UL Environment Sustainable Database to get an idea of just what it looks like. So how about some information? So here's basically what pops out. These three pie charts show three different printers that are of similar utility. The one on the far left and the one in the center are two different laser printers, and the one on the far right is a page-wide array inkjet printer. And what this is showing you is that for all these products, you can see what the breakdown is for printer production, transport, and those kind of things. What I want you to notice is that one of the big learnings for us was that we expected paper to be the biggest impact over 1,000 pages, which is what this is showing. But what we didn't realize was just how much that impact varied in moving from an inkjet printer to a laser printer. So you see for inkjet, the one on the far right, paper is about 60% of the impact. Whereas for laser printers, it's only about 30% because cartridges and electricity are much higher. So this is an example of how LCA shows you, at least for carbon, where the hotspots of the impact lie. And these are just a few representative ones for a few specific printers. But here's where it really was valuable to us. If we look over our entire portfolio, in the case of LaserJet printers, what we found is pretty much what we expected. Over the life of the product, those printers that print a lot, basically the ones on the far left of this graph, have the highest environmental impact, and the ones on the far right have the lowest. I presented this at a conference a couple of months ago, and so, this is sort of, you think, well, duh, Tom, that's what we expect to happen. And the guy on the front row actually guffawed and fell out of his chair. But the main thing here is that it shows us that the model is working. It shows us that we're getting the higher impact numbers for things that print a lot and lower impact numbers for things that don't print a lot. What's useful in some ways, but really doesn't give you that much information. Where the real aha comes and the real information is when you break it back down to that functional unit I mentioned. What does it look like when you ask per 1,000 pages? Do I have a bigger impact on a desktop printer or on an office printer? And this was a very useful set of information for us. You see, it basically flips around. Those big department printers have a much lower impact per page than the lower printers. And in some ways, that makes some sense. I mean, if you're printing 1 million pages over life and your production impact is only maybe 2 or 3x that of a smaller printer, you'd expect the per page impact to be lower. What was a big aha, though, was the fact that on a per page basis, for instance, the smaller printers had some higher impacts due to fractional impact due to electricity use, and the fact that consumables were pretty uniform across the board. So this is where it's really LCA started to help us determine where, if we're going to try to design for the environment, all else being equal, where do we want to start looking? Obviously, production or making materials changes and things like that is important, but the bigger places to start looking were in the use phase, and things like, is there a way to reduce the amount of electricity? Is there a way to reduce the amount of paper? Is there a way to make our consumables less impactful? And just to give you an idea, here's what it looks like across our whole printing fleet, with the LaserJets on the left and the inkjets on the right. And again, this was a big aha for us in many ways, because what we found was that the the inkjet portfolio, as expected, was generally lower than the LaserJet portfolio, but it wasn't necessarily in all the places we expected. We knew inkjet printers used less energy because we're not trying to fuse toner onto a sheet of paper. But the fact that it uses that much less energy as far as the CO2 goes was a surprise. The other big one, again, is in consumables. And so these are the places we've started making inroads into reducing the impact. One thing I should point out, this graph excludes paper, because 1,000 sheets of paper has the same impact whether it goes through an inkjet printer or a LaserJet printer. So we pulled it out here so you could see just how the various impacts of the printer itself affect the carbon footprint. So basically, what are our benefits and learnings to date? I should point out this is relatively new for us. We've only been running LCAs of printers for about 3 years now. So we're still fairly early in the cycle of getting this into design for the environment. We've collected the data now. Now it's my obligation and that of many of my colleagues to get back to the engineering team and start incorporating that information. But to date, we've completed about 175 printer LCAs and about 5 scanner LCAs. And as I mentioned already, our biggest learnings were, one, we need to work with our customers to help them print more efficiently. So encouraging customers to do more duplexing and so forth. To reduce cartridge impacts, basically what can we do to dematerialize a cartridge and still get the same number of pages out of it so that we reduce the environmental impact on a per page basis. Those are the two big ones. The other one, power consumption, that's something that's been driven very strongly by governments, things like the EPA, to push down power consumption. So there's not really a whole lot we can do there anymore, and it's not been something we've done as a company based on environmental impact. We've done it in large part based on what we've been forced to do by government regulation. And finally, as I mentioned, the big one is the inkjet portfolio does have a far lower impact overall than the LaserJet portfolio. So big benefits overall for HP has been that it has allowed us to be the first IT company to publish our complete carbon footprint. And I'll show you that in a minute, because that's, rather than being something that's beneficial to the product itself, it's a secondary benefit we got as a company. And the other things I've already mentioned, opens the door to comprehensive design for the environment. This particular model cut the cost dramatically for generating LCAs, which allowed us to get this information across our portfolio. And as I said, it's meeting customer demand. I get requests from account managers virtually on a daily basis asking for the environmental footprint of specific printers so that they can sell them into accounts. I quickly want to just talk about what this has done on a corporate level. Some of you may be familiar with HP's Living Progress Report. It's a comprehensive document we publish annually that covers all of our global citizenship activities, everything from economics and environmental and workforce welfare and things like that. I encourage you to take a look at it. It'll give you a very good idea of just where HP stands on all of these things. From an LCA standpoint, it's allowed us to do, as I mentioned, allowed us to report our carbon footprint as a company. But the main thing is it's allowed us to intelligently set reduction goals for carbon and for water. So you see here, as a company, our product's use phase is about half of the entire carbon footprint, which is what you'd expect. If you're doing printers and computers that are using a lot of paper, using a lot of power, that's where much of the carbon footprint comes. For something like the building products or the office products that Thaddeus mentioned, use phase probably isn't as much. The impact is much, much more on the production side. So by doing these LCAs, it allowed us to understand across the company where our impacts are so that we could set the reduction goals appropriately. And it's also allowed us to report our total water footprint, and this is another place where we had somewhat of an aha. If you look at the use phase, that's about 68%, but of that use phase, paper is a substantial portion, which was quite a surprise for us. But it also allows us again to say, okay, now this is more compelling evidence for us to work with our customers to reduce their paper usage by doing more duplexing and so forth. So what I've tried to give you here is just a very quick overview of how we use LCA at HP, at least in the printing business, and why LCA is different from some of the tools that Thaddeus and Ann mentioned. It's not so good for making direct substitutions based on toxicity, but it is very good at giving you an idea of where your hotspots are to start looking. Okay, with that, I'll hand it back.
Excellent. Thank you very much, Tom. One question, Thaddeus, you mentioned that you did all the pathways on the flowchart that you had for finding safer materials. How have you found a new material and supplier when you or the manufacturer couldn't supply an alternative?
So that can sometimes be a challenge. Oftentimes, I would say pre-2008, we used to have manufacturers come to us all the time, sharing materials that they had, chemistry they could provide. And so a lot of times we had a database of materials and suppliers. That kind of fell off for a number of years due to the economy, and I think we're starting to see that again. So a couple ways. One, people come to us and we have what's called an advanced materials team. The advanced materials team is made up of people from a number of functions throughout our company, and their specific goal is to address common problems at Herman Miller in our materials. So we may want to be addressing a sustainability problem, chemical of concern, or specific consumer problem that our customers are having. And so that team actively goes out and brings new materials in to review and help commercialize. So through that process, we tend to have a database and a library of materials we can seek out. In other cases, our team will work directly with other manufacturers that supply materials to us or our tier 1 suppliers. And we will discuss what it is we're looking for, the specific material and engineering properties, and the specific list of chemicals we wish to avoid. And then as they present alternatives, we'll then screen and assess those for their chemistry.
Great, thank you. Another question, are there any alternative assessment examples that are publicly available?
Let's see, I believe at Green Screen there are some alternatives assessments and green screen assessments, the Green Screen website, which can also be obtained from Clean Production Action or BizNGO. And I believe also the Interstate Chemicals Clearinghouse provides some alternatives assessments that are available. Within ChemHat, we link to Subsport, which is a European database of case studies of safer alternatives available. So you can go to Subsport, we can provide all those links, or you can go through ChemHat to the Subsport link if you're looking for you can search on an individual chemical and see what stuff is there. We have something like 10,000 chemicals in ChemHat, which is built on the Pharos database from Healthy Building Network, and it's something like 500 case studies of safer alternatives. So there's still a big gap there, but there are a few here and there. Are there others, Saskia? You probably know of some that I have forgotten.
I think you covered the main ones. Washington Ecology will be putting together a website, but actually the IC2, which I think Topher is actually going to put in the chat box, he has a link, is pretty comprehensive. Another question, Tom, you mentioned the way that you use your tools. Some of it's based on kind of standards that are available, and some of them are based on data that you have from your companies. Have you found that there's been a voluntary increase in your manufacturers providing that data, or do you require it? How do you get that data?
We have found that there's been a voluntary increase, and we've been able to show them how it's benefited us through this LCA work, and also it's been more forthcoming just in general, I think, across our business. So there are several public databases out there. There's the US LCI database, and there's some available tools such as SEMA Pro and others which tap into the databases as well. And I think a lot of manufacturers are more freely putting information into those databases for folks to use to do life cycle assessment.
Okay, great, thanks. Does Hewlett-Packard use life cycle assessment to evaluate anything other than carbon and water footprints of its products?
We do, but we don't put as much weight on it as we do for carbon and water. And the reason is that for many other things like aquatic toxicity and others, there are tools out there which we feel are better. And so Green Screen is one that we use extensively, and some other tools. So we do use it to look at where the hot spots for many of those things are. Once we determine that, we use other tools to determine how best to address those.
Great.
I have a question for Thaddeus. I was curious about your fiberglass chairs. What proportion of those are coming back for recycling?
Yeah, that's a good question. And right now, none that have gone out to the field, quote unquote, so sold to a customer. We do have internal chairs that we've tested for green guard or other things where they need to be disposed of, and those have gone back to the manufacturer to be recycled. But this particular chair we invented and we're selling it in the 50s, and some of those chairs, lots of those chairs are still in existence. So that it's not a chair that should or will break very easily. So hopefully we don't see a lot of those back. We only started selling the fiberglass version a year or two ago. Again, we reintroduced it a year or two ago. So they're very new in the field. I don't think we've seen many of those come back, but our corporate goal over the next 10 years is to take back 50% by weight of all the products that we make. So we do anticipate additional programs to take back other products, whether they're at their end of life or a customer is just doing a refresh and wants new product. So we're going to be seeing a lot more of that, and we're still trying to figure out how to make that all work.
Thank you. A testament to the longevity of your products.
Do any of you have additional questions for each other?
I have a question for Tom on LCA, and something that I'm thinking through right now is how has Hewlett-Packard, if you've done this, looked at the impacts that you're presenting in your EPD or internally or elsewhere versus Hewlett-Packard or the printers industry impact on national emissions. So let's say you're reporting global warming potential, and is that a significant impact for your industry? Does your industry have significant impact nationally, or is that really not an issue for the printer industry or Hewlett-Packard in general? And I'm wondering if you thought through that for the various impacts you do report on.
That's a very good question, and we have looked at quite a bit of that. One thing, the IT industry in general is among the less impactful globally. Heavier manufacturing is higher, and energy production is higher, and so forth. So I don't know at a corporate level how we've looked to see how we compare there. We certainly look to see how we compare within our industry and related industries. We're using that in part to understand where does it make the most sense for us to reduce as well. There is some information along those lines in the Living Progress report that I mentioned, where it does compare us to other industries and others within our industry to give you some of that information. So the short of it is that yes, we do some of that, but we're still looking at it more from how we can reduce our impact in general rather than how ours compares to other manufacturing.
Thanks. And one specific question, the Eames chair from Herman Miller still has foam with flame retardants, or is there one in the marketplace that's coming out without?
Sure. So that's a question about flame retardants. We have always tried to take flame retardants out or use the safest possible. We couldn't always take all flame retardants out based on the California law. Of course, the California law has now changed. So we had a corporate goal to remove all flame retardants from our products by June of this year. And I would say that we're 95% there. So I'm not sure which Eames chair. We have a number of Eames chairs that are upholstered. I'm going to assume it's the Eames lounge chair and ottoman, which did have halogenated flame retardants in it. And those are scheduled to be removed in the next month or two. So we have already identified alternatives. They're already approved. They just have to go through all the engineering change order so that we can get that material into the plant and begin incorporating it to our product. So another month or two. I think the date was September 1st for us to completely change over to flame retardant free for the Eames lounge chair and ottoman. If it was a different product, definitely contact me. I can give you the scoop and the timeline on any of our products and where they are with flame retardant removal. So if you look at any of our other seating products, our high-end task seating products, I believe those by the 1st of July, the last one of those should be completed.
Great. I guess I got a response of yay. So I think you covered the question well. Another question, it's a two-part question. What is the level of knowledge chemists need to have about these tools, and how can they work effectively with experts on LCA and AA?
It varies by the tool. There are many tools. The ChemHat tool, for example, was designed for workers who knew about the chemicals they were working with, but not necessarily in great detail, and it was a way of handling sometimes conflicting and confusing information on toxicity. So there are tools out there that are designed that can be used by non-chemists, I think. What it says is, here's your highest risk, here's how you can protect yourself, and here are safer alternatives. Green screen, probably, I'm getting varying reports on how much of a chemist you need to be to use it. It is designed, there is also the QCAT tool, the sort of shorter version of green screen that was created by Alex Stone at the Washington Department of Ecology that I can, Saskia and others, you can offer your opinion on whether you don't need to be a chemist to use that. So I would say it varies by tool. There are tools available screening tools like the retailer screening tools, really you don't need to be a chemist to do that. Good Guide was designed for the same way that you don't need to have a PhD in chemistry to go shopping in the grocery store. So there are some out there that require more chemistry background and some that don't.
My background's chemical engineering, and I think for a lot of the tools that we happen to use, you don't need a chemistry background, and we certainly have some people on our team without a chemistry background. But it definitely helps when you're using these tools and you're looking at chemistry that's in a product. It does help to at least be familiar with the basics of chemistry and perhaps organic chemistry, just to make it more clear what's being assessed and looked at, but absolutely not necessary. If you didn't have any, coming from a manufacturer standpoint, the detail that we go to look at materials and chemicals, if you don't have a chemistry background, you're probably going to spend some time doing some reading and understanding a little bit to be effective. Definitely possible. And I'll let Tom answer LCA. I can kind of give my opinion, which is chemical background completely unnecessary for life cycle assessment. It could help. I think what helps more is having some sort of idea of what happens during manufacturing processes and having some sort of manufacturing background. Again, helpful, not completely necessary. But Tom, you can also chime in.
And I agree with that. The only place, so I'm a chemist by training, but I found that I've not needed to use it very much as an LCA practitioner. Where it has come in handy is that when you look at the databases I was mentioning earlier, the database for complete life cycle inventory for chemicals, for many of this, there isn't as much out there as there is for a lot of other things. And so having a chemistry background can be helpful to know that, okay, if I can't find chemical X in the database, but I can, what can I find that's close enough to at least approximate the impacts and make those substitutions. But generally speaking, I agree with Thaddeus. It's not that necessary.
Great, and I'm going to add another comment because the question also kind of got flipped a little bit. It was actually the level of knowledge that chemists, I'm assuming it was designer chemists, need to have with these tools. And I would say that, it varies really depending what the position the chemist has. But also another thing that is hard about that question, it also depends on the resources that chemist has available, because it's possible if they have a coworker in, toxicology, that they might not need to know as much about it. Really depends on your team. But I guess the question is, if you were a designer chemist or someone, further up the supply chain, how familiar would you want them to be with these tools? Because I'm assuming that would be one of the ways that they would actually work with your teams.
My ideal preference would be that they are intimately familiar with alternatives assessment and the tools that are out there, because again, we have some chemical knowledge and some expertise within our company. We have a number of chemical engineers that work on our team, but we're not experts. We don't manufacture the raw materials, and we don't manufacture oftentimes the parts, and we're buying those from a supplier, and we're assembling and doing the design. So we really rely on our supply chain to be the experts, and the more knowledge they have that can help us think through and find alternatives, the better.
Great. This is another two-part question. In practice during the AA process, how early is the need for chemical material innovation or new technology usually identified?
Oh, I don't know that this is advanced a practice enough to have a usually yet, but I would say the earlier the better, and it really very much depends on the context that we're talking about. If we take, for example, the 3 priority products that were identified by the state of California, in some cases, if you think about first flame retardants in children's products such as nap mats, when you ask the question, is it necessary, the answer is pretty easy. I don't know too many kids that are smoking in their cots. So that was an easy answer, and these choices were designed that way in some ways. The second priority product was methylene chloride in paint strippers, where there were alternatives readily available and have been on the market and utilized for some time, including the regrettable substitution that I mentioned earlier of NMP. And then the third one is spray polyurethane foam with diisocyanates, which is a huge worker exposure issue, where there really isn't a clear chemical alternative. There are obviously alternatives for insulation in buildings. So in each of those cases, I think innovation is probably more necessary in the case of spray polyurethane foam than the other two. So it varies hugely by the context and the product and chemical in question, but I would say the earlier the better.
And this is Thaddeus, and I'll just say, in practice, where do we usually find out we need an alternative? And even though we've been doing this for a long time and we're redesigning our process to get better, oftentimes it happens late in the process when the design is finished, the engineers have selected properties, and a supplier has selected a material. And then we find out there's a chemical of concern in a specific material, the molds have already been cut, everything is kind of moving forward, and it's much harder at that point to push in an alternative. So again, as Ann mentioned, the further up the product development process, the better for us. And that's part of what our advanced materials team's job is, to identify better materials, get them to a point where they're kind of sitting on the shelf and ready for an engineer to specify into a product. So the practical applications, oftentimes, companies like us, we're producing and getting so many products launched all at once that it can often be hard for a small team to monitor every single development. And getting the right tools to the right people's hands early is absolutely critical.
Great, thanks. So the follow-up question, which is the final question, when there has been need for an innovation identified, what are the avenues for a company to communicate this information?
I'll let Ann go after me, and maybe Tom, if you got some ideas. This is Thaddeus. I think we struggle with doing two things. One, finding alternative materials and chemicals, because we just don't know everything that's out there, nor is there a place that we know of to go and search for those. And the second thing that we struggle with is, once we have a need, and we've identified, let's say, a need for no flame retardants in a polyurethane foam, but still needs to meet the more stringent Cal 133 flammability standard for both California non-sprinkler buildings in Boston, how do we communicate that to the right people that that's a need, and the right chemists at the raw material stage can find a solution and present it to us? And of course, there may be more, and there should be more than just one company that's looking for some of these solutions, but it doesn't always bubble up to the people that can create those solutions.
I would agree with Thaddeus on that. I think there's a huge gap here that needs some work. I work with a lot of small companies that are trying to put new formulations, ingredients, or materials on the market, and they hit all kinds of interesting barriers, and there's no one central place, as Thaddeus mentioned, for any sector to go and look for safer alternatives. And I'm working across a bunch of different sectors. There are two examples that I think would be good models, and there may be others that you can think of. Well, three actually. So GC3 has one where they've taken a particular problem in a specific industry and dealt with looking for safer alternatives, and that has provided a point of a node, as it were, for information to come together, and that was looking at phthalates in wire and cable applications. And there may be some efforts to look at preservatives as well in cosmetic and cleaning formulations. Another model has been an academic model, which is UC Berkeley Center for Green Chemistry's Greener Solutions class, which is a graduate level cross-discipline class that's been running for 3 years now, and 2 years with partnership from the Biomimicry Institute. And individual companies in some cases, or several representatives of a sector, have come in with a specific problem. Textile finishing was one. Levi Strauss worked with BCGC and the Biomimicry Institute, and then subsequently an issue of preservatives as well, and then the issue of spray polyurethane foam that I brought up earlier. And so then you have these graduate students, cross-disciplinary graduate students, looking for types of alternatives and ideas for what could be researched as a result of that, biomimetic solutions. A third example is the American Chemical Society's pre-market roundtables, I think, for formulators and pharmaceuticals. So that's one where specific industries come together and say, here are the issues that we're dealing with, chemical issues, and we're all dealing with them, so let's have a pre-market discussion about what some of the solutions might be. So those are the examples I know of, but it is still, as Thaddeus has said, is a huge problem for many sectors to know where to go to look for safer alternatives, and for companies that provide those alternatives to provide that information. So we need your ideas on how to do that.
With that, I'd like to thank everyone for joining us. Thank you very much. Appreciate your attendance, and thank you again very much to the speakers for a wonderful presentation.
Thanks, Saskia.
Thank you.
Thanks, everyone.